Good morning and welcome to Physics Studio. What I'd like to talk about today is color and what it means to see something. And we're going to find as we look at that there's some odd things about the way we perceive color that are not quite covered in the textbook. And we're also going to find that the world itself is a colorless place. So let's take a look first at what's happening with the wave phenomenon. Now, we have what we call objective phenomena. That means things that are out there in the world, and sound and light are objective phenomena in the sense that they have a frequency and a wavelength, they have an amplitude, they have a wave speed. However, we also developed and evolved over millions of years apparatus to get information about the environment from those waves in the form of their frequency and amplitude. And when we receive that information, unlike a computer with a camera, which can also analyze that information, we get a picture in our head, right? A vivid picture forms. We call that a subjective sense. And for sound, frequency and wavelength are perceived as pitch, as in high and low notes. In light, the frequency and wavelength are perceived as color. The amplitude is of a sound wave, right? The size of the oscillations, the size of the deviation from ambient pressure is perceived as loudness. And you can probably guess by analogy that the amplitude of a light wave is perceived as brightness. Right? You would never be hurt by a certain pitch or color of light, but you can be hurt by loudness and brightness. Now, once we've established that, the question about whether you can hear, if a tree falls in the woods and no one's there, does it make a noise? Objectively, yes. Subjectively, no. Now, let's turn to light and the question of how we see. Now, first we're going to get something that you picked up in grade school. Okay, I'm going to make a little graph here. And we're going to call this wavelength in nanometers, which are billionths of a meter, or 10 to the minus 9th meters. And we'll call this, let's say, 400, 450, 500, 550, 600, 650, 700 nanometers, right? So from short wavelength, high frequency, and this is high frequency, and this is low frequency. Now we perceive, this is the visible spectrum of light here, really from about 380 to about 720 nanometers. It's a very narrow range in the electromagnetic spectrum. But we perceive light over here as red, orange, yellow, green, blue, indigo, and violet, which you're familiar with. Out here, beyond the violet range, we have ultraviolet, then X-rays, and gamma rays, where you get up into extremely high frequencies and extremely short wavelengths and high energies. Down here, off the visible spectrum, past red, we have infrared, microwaves, and radio. Theoretically, onto infinity in both directions. And that's the electromagnetic spectrum. We only see this tiny slice right here, ROYGBIV. Now, let's take a look at what it means to see an object. Okay, there's two types of things in the world. There are sources of light and other things. And if we have an object in the world and there's no light source, we don't see anything. Right, so to see something, you need a light source, like, for example, the sun, or the light in your room or anything like that. And the sun and other light sources put out waves in all directions, electromagnetic waves. And as this travels 93 million miles, right, from its extremely high intensity here to its lower intensity here, some number of these waves are going to strike this object here, right? And I'm going to divide this up. This is really how it would work, but let's say we've got red, orange, yellow, green, blue, indigo, violet, right? Because white light is composed of all frequencies. That sunlight's going to hit this banana here, right? And what's going to happen is some number of these in the middle, or on this end here, the blue, indigo, and violet end are going to be absorbed, right? They're going to hit the banana and they're going to be absorbed. But some number of these are going to be reflective, and they'll reflect in all directions. And so we've got the green light reflected, and the red light reflected. And over here, if we have a perceiver, some amount of that light's going to enter their eye. And so this light of a particular wavelength, right? Right, the banana is absorbed down here, so we've got some combination of green, yellow, orange, and red frequencies. When that hits the eye interprets those frequencies as yellow, and bam, a vivid sense of yellow appears in our minds, that picture. We don't really know why that happens. And similarly, for example, let's say we have a leaf. And we have sunlight coming in. From red to violet, orange, yellow, green, blue, indigo, violet. All these frequencies are going to be absorbed. Right? The chemicals in the leaf itself, the chlorophyll, etc., they're set to absorb certain wavelengths of light. This particular wavelength, though, is going to bounce off. And anyone who perceives that, a camera, a person, an animal, will perceive that. And the brain will send a signal. That's why we see green leaves. Now, in art history, through the mixing of pigments, they came up with the idea of primary colors. Sometimes that's glossed as red, yellow, and blue. And sometimes it's glossed as RBG, red, blue, and green. And the insight is that if you have three primary colors, you can mix them in combinations to form all the other colors. Now, we've found that inside the human eye, there are 3 color receptors or cones, and your book glosses them as red, blue, and green. In fact, what these cones do is they absorb light at certain wavelengths. So we have one that really strongly absorbs light around there. We call that the high frequency cone, or call that low wavelength. And we have another one that absorbs very strongly around right here. We call that the medium wavelength cone. This one, its peak sensitivity is at about 419 nanometers. This one's about 531 nanometers. Now, if you were an intelligent designer, right, you've got your indigo or your blue, you've got your green, you would probably put another one out here in red, right? But in fact, the third one has a peak sensitivity about here. We call that the short, we call that the long wavelength. So sorry about that. This is short wavelength, medium wavelength, long wavelength. And this one has its peak about 561 nanometers. So if you saw light at this frequency, you would see that as somewhere around indigo to violet. If you saw light at this frequency, it would appear green. This frequency is apple green. So there is no red cone receptor. And we don't have a yellow cone receptor. We don't have an orange cone receptor. But what happens is if light primarily at this frequency here strikes the eye, it's going to activate the long wavelength strongly. The short wavelength much less, the medium wavelength much less, and the short wavelength hardly at all. And then suddenly a yellow image will pop into our brains, right? So it's not that we're seeing yellow. Now, all these frequencies are identical except for the speed that they oscillate at. And so the only difference is the frequency of repetition, which is a mathematical number. But our brain doesn't send a number to tell us that, right? It sends a color. And so if you look, for example, at some colorful object, you might think that there's a red stripe in that blanket. But in fact, all there is a pigment that absorbs most of the wavelengths except for the ones over here. The blanket itself is colorless. Now, last question is, you might wonder why we have this kind of a setup, and that's a problem for evolution. It appears that most birds, reptiles, and insects have 4 color receptor cones, and they call that tetrachromatic. Sometime during the period of the dinosaurs, mammals lost 2 of those, and so most mammals only have 2. They're dichromatic. So a dog or a cat's experience of color is much different from ours. Now, sometime about 36 million years ago in old world monkeys, of which we are descended in these terms, a third one was duplicated and began to diverge from the medium length. And in 30 million years, it's only had enough time to diverge this much. But in another 30 million years, that cone may be all the way over here. So anyway, that's your tutorial on sight. And we wanted to bring up the point that A, objects in the world have no color. That's an artifact of our perception. And B, it's not exactly accurate to say that our cones are red, blue, and green. They're really red, green, and apple green, but they do the same thing. So anyway, enjoy your investigation of color, and I'll look forward to see your discussions.